This is recitation 8, problem 4. Now we will consider a wire with current I, not just a single particle, but a wire with current I. And if we have a wire with current I, and we place this wire in a magnetic field, then there will be force exerted on this wire. And I will write it as dF, infinitesimal force, exerted on infinitesimal piece of this wire with current I. ds is infinitesimal length cross magnetic field created in this region, in some region of space. ds has magnitude ds, and the direction of ds is the same as direction of current. Now we will solve this problem, and this problem is again from Don't Panic book by Bill Basikas. For this problem, we have a metal wire of mass m. This wire has given mass m, and this wire can slide without friction on these two parallel horizontal conducting rails. The rails are connected by a generator which delivers a constant current I. There is a constant vertical magnetic field perpendicular to the plane of the rail. So the rails are in the plane of the board and the magnetic field is up perpendicular to the plane of the rails. If this wire is initially at rest, find its velocity as a function of time. We need to find the velocity of this wire as a function of time if velocity at time moment 0 was 0. Well, from mechanics, we know that if we find the acceleration of this wire from second law, if we know the acceleration, then we can find the velocity, because the velocity, to find velocity, we will just integrate the acceleration. So why don't we try to apply the second law to this problem? What is the force acting on this wire? Gravity will be equal to the normal force. I will draw this wire coming out of the page. This is side view. So this wire is coming out of the page. This is cross-sectional area of this wire that faces me. Then the current is coming out of the board. Current is coming out of this board, which means that ds is out. This is ds. ds is in the same direction as current coming out of board. B is up. We start these vectors from the same point. So what is ds cross b? That's what we need to find. To find ds cross b, you need to use your right hand. I use my left hand because what you see is my mirrored image. I put my fingers along ds. I bend them towards b, and my thumb shows the direction of the force. So the force will be to the left. I will use this color to draw the force. This is my magnetic force exerted on this piece of wire. This is the direction of the force. What is the magnitude of this force? I forgot to give you the length of this wire. The length of this wire was given. It is L. Then magnitude of this force is current I. Length, magnetic field, is the same at each point of this wire. It's uniform. So the integration is trivial. Integral ds is just length of this wire. Length is in the plane perpendicular. The wire is in the plane perpendicular to the plane of the board. The magnetic field is up. So these two vectors are perpendicular to each other, which means that cross product is just product. This is the magnitude of this force. And then ILB, I write Fx now, Fx max, where my x is to the left. This is my direction, x. X is to the left. Then projection of force is positive. I write ILB, positive ILB, the force, and this is equal to MAX. Acceleration, the acceleration AX is current that is given, L is given, B is given, and M is given. And all I need to do now, I need to find the velocity, which is integral AX of t dt. But look at this, acceleration is constant, so integration will give me just ILB divided by M times t plus velocity at time moment 0 plus constant, which is velocity at time moment 0, velocity at time moment 0, which is 0. So we found the velocity of this rod as a function of time.